All right, welcome. Today, we are cracking open one of the most fundamental particles in the entire universe, the proton. And I gotta tell you, what we're about to find inside is going to completely upend what you probably learned in high school physics. It is not just a simple little trio of quarks, it's a chaotic quantum world that is so much more fascinating. So let's dive in. So, let's start with that big question. What is really inside a proton? If you could just somehow grab one and break it open, what would actually fall out? Well, the answer, it turns out, is both incredibly simple and impossibly complex, all at the very same time. Now, this is the classic picture, right? The one we all remember. A proton is made of three quarks, two up quarks and one down quark, all bundled together. It's a nice, tidy little package, and honestly, for a lot of things, it's a perfectly fine way to think about it. Yeah, not even close. In the world of particle physics, things are almost never that simple. That three-quark picture, it's really just scratching the surface. To see the real proton, we have to zoom in. Way, way in. And that's where things get genuinely wild. To really get what's going on, we need to introduce a new word: partons. This is the key that unlocks the true, hidden complexity of the proton. We're about to leave that tidy world of static little particles and plunge right into a seething, chaotic sea of quantum activity. So, what exactly is a parton? Well, it's pretty much just the catch-all term for everything that's inside a proton. Think of it like the entire population of this tiny subatomic city. You've got the quarks for sure, but you've also got the gluons, which are the particles that act as the glue holding the whole thing together. And here is where it starts to get really weird. As the source material says, partons are not naked particles. What does that mean? It means you can't just isolate one, you can't put it under a microscope. Their very identity, and get this, even how many of them there are, depends entirely on how you look at them. This leads us to this totally mind-bending idea called scaling violation. Put simply, the more energy you use to smash into a proton, the more stuff you find inside it. It's kind of like looking at a coastline on a map. From really far away, it looks like a nice smooth line. But the more you zoom in, the more jagged edges and little details you see. The proton, it turns out, is the ultimate quantum coastline. And this slide just nails that duality. On the left, at low energy, that's our low-resolution view. We see those three classic quarks we talked about. But on the right, when we crank the energy way up, like in a particle collider, we get the high-resolution view. And it's a frantic sea of quarks, anti-quarks, and gluons constantly just winking in and out of existence. It's the same proton, but it's like two completely different realities. Okay, so if a proton is this absolute chaotic mess, how on earth can physicists possibly test their theories? How do you find a clear, reliable signal in all of that noise? I mean, it seems impossible, right? But they have a very, very clever trick. The answer is to look for a very specific, very clean event, a standard candle, if you will. Just like astronomers use certain stars with a known brightness to measure vast distances, physicists use a particle called the W boson. Its creation and decay give them a perfect, unmistakable fingerprint that cuts right through all that chaos. Let's just quickly walk through this. Imagine two protons smashing together. A quark from one proton meets an antiquark from the other proton's chaotic sea. Poof! They annihilate in a flash of pure energy. For a fraction of a second, that energy becomes a W plus boson, a carrier of the weak nuclear force. But it's super unstable. Almost instantly, it decays into other particles that scientists can easily detect. It's that clean chain of events that they're looking for. Now, just seeing that fingerprint happen is one thing. But here's the most amazing part. Physicists don't just see this happen. They can predict, with incredible accuracy, exactly how often it should happen. And they do this using a kind of mathematical recipe that's built from the fundamental laws of the universe. And this isn't just, abstract math. This recipe connects the deepest truths of our reality, the fundamental strengths of the forces that govern absolutely everything, directly to something we can actually measure in an experiment. It's like a bridge from pure theory to observable reality. So these are the key ingredients in our recipe. You've got constants that basically set the strength of electromagnetism and the weak force, and then the Weinberg angle, which kind of links them together. These aren't just random numbers. You can think of them as the fundamental settings for our entire universe. If you change them even a tiny bit, you would get a very different reality. Okay, here it is, the heart of the recipe. Now, don't be intimidated by this equation. You do not need to solve it, I promise. The whole point here is just to understand what all the pieces represent. This formula is the tool that tells physicists the exact probability of a quark and an antiquark smashing together and creating a W boson. So let's quickly break that down. Each part of that formula tells a little piece of the story. That V term, that's about the probability that the quarks will change their flavor or type. The G term is the raw strength of the weak force itself. That M term has to account for the energy you need to create a really heavy particle like the W boson. And those fractions, that's just physicists averaging over all the random quantum possibilities. It's a complete description of the event. So we've dived super deep into the quantum weeds, right? We've talked about chaotic seas and complex formulas. But why? What's the big picture here? What's the payoff for all of this incredible, painstaking detail? This is why it all matters. When physicists at the Large Hadron Collider smash protons together millions of times a second, and they count up how many W bosons they see, and that number perfectly matches the number predicted by the recipe, I mean, wow. That's one of the most powerful validations of our entire understanding of the universe. It's where theory meets reality and they shake hands. So let's do a quick recap of this journey. We started with that simple three-quark proton, and we discovered it's actually a chaotic quantum sea. We learned that what it looks like literally changes depending on how we look at it. We found a clean signal in that chaos, the W boson, and we saw how physicists use a super precise mathematical recipe to predict its behavior. And that leaves us with a final and kind of mind-bending question. We've just seen that a fundamental particle of matter doesn't have one single fixed identity. Its reality is defined by our interaction with it. So, what does that say about the line between us, the observers, and the universe we're observing? What does it really mean for something to be real? Thanks for joining this deep dive.